My name is Peter Morgan. I'm from William Hill. I'm going to talk about an evolution of a betting engine that we have been building in Erlang. I'm head of engineering, and I'm also head of research and development. So part of what my team is doing is looking at different ways that we can build systems that we currently have within William Hill. So William Hill, we have around a peak, around 464 bets per second being struck in the system. We have about 160 terabytes of data that goes through our networks on a daily basis. And we're also a 24/7 business. We don't have much opportunity to actually shut the systems down. We trade globally. The other interesting thing is that our prices change. We have around 5 million price changes a day. That doesn't sound like a lot, and I know if you're doing high-frequency trading and things like that, you're kind of thinking, well, we do that in a femtosecond or some other amazing number. So this is betting. It isn't high-frequency trading. 5 million for us is a large number. The only thing I will say about that is that a lot of those price changes will happen in a 90-minute window because they're football price changes. And they're also affecting a large number of bets as a result. So what does it look like? This is our bet stream. It's actually 5 seconds of our bet stream, and it's a visualization that we use. It's Visual Viz.js that we're actually using here, and it's taking a stream of bets from William Hill on. This was Saturday. And you can basically see a graph of what bets have been placed by our customers in that 5-second period. And what you've got is a hierarchy of bets. So you can see a customer in yellow. You can see the actual bets they're placing, which are the blue circles. And then you can see the actual selections that customers are betting on. So mini clouds, Mont Royal. These are all the different selections that customers are placing bets on. And we can basically run this stream live. And it's a great way of explaining to people the kind of complexity of the data that we have. So you can see this is essentially betting on horse racing. You can see all the customers who are betting on the 410 at Weatherby. And you can see all the customers who've placed a bet on many clouds. So it's a dynamic structure that's being created. It's really for visualization. It's purely so I can explain to my manager that this is quite hard, because it's quite hard to explain otherwise. But we also print out T-shirts. So if you want a T-shirt later on, Gavin has got the T-shirts. So you can see bets on the rugby union. This was before the rugby union final on Saturday. So I picked out some rugby bets, but rather stupidly, I didn't pick out any that were any to do with the actual rugby union final. But you can see a cluster of rugby union bets here. You can see that people who are betting on rugby union aren't actually betting on other kinds of sports. And this person down here is the only person who's betting on tennis. So it's interesting from the perspective of how the customers bet, and looking at the kind of topology of the bets. And again, if I didn't explain it very well, yellow is the customer, blue circle is the bet, and then you have selections and then the different bits of our hierarchy. Now, the interesting bit is this bit here. This is football. And the majority of our business, like most gambling companies, the majority of our business is football. So you can see a bunch of bets here on the European major leagues. Here you can see, where is it there, a bet on the next 5 minutes. So we have lots of very ephemeral markets. So at the moment we offer 5-minute markets. We're looking at ways that we can offer 1-minute markets to customers. So who's gonna have a red card in the next minute? Those kind of things. So when we combine the price changes that we have together with the availability of the markets that we have, typically on a Saturday we have about 100,000 markets. 400,000, and we're looking to get it to 400,000. It's pretty large. The other thing about football, it's all about accumulators. So here you can see a single bet, and as I'm highlighting them, you can see the variety of selections that it affects. So when I talk about that 5 million price changes, if it's an accumulator bet, that can be affecting a very large number of bets. So the 5 million is multiplied by another number, which I can't tell you. So that's what our structure looks like. And again, it's a toy. It's just to show people what things look like. So a little bit of context, because I'm guessing not everybody has placed a bet today. No. So where does this kind of fit in the whole piece? So a little bit of our sort of terminology. We talk about placement, we talk about resulting, and we talk about settlement, and pretty much in that order. So placement is going to our website, for example. So here we are on our horse racing page, placing a bet on our new website. We also have 2,500 shops. So our customers can be placing bets in our shops at the same time. So writing down their bet on the bet slip and then handing it over to the teller and for it to be struck that way. Then after your bet is placed, we allow you to cash that bet in. So you might have changed your mind, so we offer to buy that bet back, or you might have won a little bit and you want to cash the value of some of that bet back. So we offer that as an option. And one of the things that we need to be able to do is revalue the price of those bets. So again, those 5 million price changes affect selections, which affect the actual bets themselves. Then the next thing is resulting. So resulting is really simple. Horse X selection has actually won the race or lost the race. And that's the input that goes in to settlement. And this is what we all want to see, a nice big case of cash. So settlement is paying out the customer, paying out their winners with the winnings to the customer based on the results that have been declared. So I was talking about the fact that I head up the research and development team. One of the areas that we're very interested in at the moment is around the customer experience. So we're taking as input prices and results. We're looking at bet placement and we're looking at settlement. And that's all centered around the actual customer experience. One of the key things that we want to be able to do is keep customers in that loop, be able to keep them notified as things change. So as your horse comes in for a win, we want to be able to tell you that. And traditionally, at the moment, bookkeepers are very much, it's a pull. If you're sat watching football on a Saturday, you've got an accumulator, you're actually updating your app. You're having to ask William Hill or whoever your favorite company is what the status of your bet is. And what we want to do is turn that on the head and make it more of a push. So, for example, everybody's got an Apple Watch, or watch, whatever we're supposed to call it now. What we want to be able to do is push data out to those devices and actually tell you, this is the value of your bet. This is the status of your bet. This horse has won, this horse has lost. Would you like to cash in at this value? All these things. Very much push rather than pull. So what does that look like? Well, scary. Very, very general sort of terms, very 20,000 foot, 30,000 foot high level. Starting right to left, let's go. Most of what we do is feed driven. And by that, I mean that we have people in this various stadia actually keying in the score as the score is placed, actually keying in the fact that Rooney has kicked the ball towards the goal is an actual message that comes into our system. If you're a tennis fan, then the umpire is actually keying the results in on a keypad, which goes into one of our computer systems. So we get feeds of data from various different providers. They go into our global trading platform. And that global trading platform then talks to a number of trading models, which are basically statistical models that basically analyze the market and then determine our current price. And they're also increasingly simulation-based. So what we'll do is we'll play out a football match from that point, have 1 million simulations of that football match. Depending on who's winning and who's losing as a result of those simulations, we then have a price. At the top is omnichannel, so that's our language for a bet that's struck on an online environment or in our retail environment. And then the key areas that I want to sort of talk about today are around the betting engine itself. So this data is fed into the betting engine, and the 4 key components of that are bet capture, accepting that bet, cash in, being able to price that bet so you can then cash it in, settlement, when the results come in, we can actually pay out the right amount to you, and liability, which we're quite interested in because we want to know how much we've got to pay you. And then sort of as a couple of examples, we've got some streams that come out of this system, and this is very much a stream-based system. So we stream out results from the betting engine. We stream out into analytics and wallets, as an example. So what do they look like? So this is our bet stream. So it's the same stream that you saw, but it doesn't have the pretty graphics. And essentially, it's a URL that you can curl. It's a server-sent event stream, which is kind of the unloved child of WebSocket. But it's quite nice because you can just curl it, and it's nice and simple. It presents a JSON-based object that you can just connect to. And it's actually, I think, one of the more useful things that we've probably done in the last couple of years is just being able to present our bet stream in a way that has no ceremony whatsoever. You can essentially use this stream in a variety of different applications. So you can see here a bet that's been placed for £10, and you can see the various different categories that that bet has been placed on. Then the output of this bet engine is another stream, and this is our bet pricing. This is our settlement stream rather. So this is as selections are resulted. What we do is we look at the bets that are actually affected by that selection resulting, and then you can see the current price, the value of that bet, whether or not it's won, whether or not it's lost, whether or not it's unsettled, whether or not it's a refund. And again, it's a really simple system that allows us to then compose other applications on top of these streams. And that's kind of a theme that I'm trying to get across here, that we're trying to do minimal ceremony for these kind of systems. And what we are thinking about are ways that we can then join these streams together to produce further applications from it. So another stream that we have is our cache evaluations. This is a lot more chatty usually, although it's stuck right there for some reason I don't quite know. It's a lot more chatty. Essentially, whenever a price is changed, then what this is doing is recalculating the value of the bets that are affected by that price change. And what we want to be able to do is take this stream and feed it into other systems, or take this stream and feed it into something that goes onto your watch. One of the key components that we're looking at for this is Apache Kafka. I'm trying not to say it's an ESB because it's not an ESB at all in any shape or imagination. But you can consider it as a distributed, replicated commit log service. So it's really, really dumb. It's really, really fast, which is really, really cool. But it's also sort of our mechanism of being able to get persistence, because a lot of what I'm talking about we're going to do in memory and rely on Kafka to actually replay what we're doing. So in general terms, we see activity going through Kafka, and then product that we can build from that. And in this case, if we have a stream of both bets, prices, and results, then we can generate streams of output, which are settlement and the cash-in values. And in another case, we can take the output from settlement and feed those transactions into a wallet. And we're using Kafka as our persistence to essentially persist any transaction that comes out of the system into Kafka. And again, we could produce another stream, which is our liability. So if we take different streams of data, we take our bet stream, our settlement stream, and our prices, then we can produce liability. So a bit more detail about our bet engine and how we built it and the kind of problems that we've had. We've built this system in Erlang. It's a pretty small team that's built it, 4 or 5 people. It's been rewritten about 5 times, about once a week normally is about our normal iteration at the moment, it's good. I mean, it kind of proves out a lot of what I think is good about Erlang, that you can basically proof of concept things very, very quickly, build things, and actually test them out. And one of the cool things is with the streams that you've seen, they're all production streams. So what we can do is we can run this system, we can A/B test it, we can run against the current system, we can run against the system that we're building, and we can test it against the rewrite that we've just done this week. So the main areas that I'm talking about today are in particular around cache-in and settlement. What do we build? Well, you've seen the stream. You've seen the stream go into Kafka. And then you've seen the Viz.js sort of visualization of that. Well, that's pretty much what we build in Erlang. You can think about all of those pieces as a process. And that's the first iteration that we took. So I love this diagram, picture. I think it's a great one to sort of represent each individual process. A lock in front of it, you can't touch its state. Each mailbox has got a mailbox where you can put the mail into. And that's pretty much the way that we have modeled the initial version that we built. And the way that we did that is traditional OTP mechanisms, nothing exciting, nothing wild. We use supervisors, we use workers. And we also considered, but we haven't done, is using a mechanism of distribution within Erlang. We're not actually using that. But it was another rare area that we thought we might be able to go. So the great thing, location transparency, be able to send messages to a process and get it to settle. Another sort of ethos that we've had is our volumes aren't that big. You high-frequency trading guys, you kind of, really that many? It's not that big. We have some of our bigger transaction days, we might be looking at 8 gigabytes of bets. So it's very much something that we can fit in memory. So I saw this slide earlier today. I think it's a great slide. What we were thinking of is really how can we make this system fast? And then what we do is we use Kafka to provide some of the resilience for us. So what we've tried to do is keep everything in memory as much as we possibly can, and then rely on another system. So we rely on Kafka to then be able to replay the system. So if we have a crash, we replay from Kafka. A lot of what we've done is basically trying to ensure that the system is able to restore itself quickly after a crash. So the basic concept that we had was, if you imagine a horse racing event, Leicester at 3:30, we have a win market, we have a horse called Fat Sota, which never wins, and a whole bunch of bets that are attached to it. And if you think about the Grand National, it's the big race of the sporting calendar. The number of processes attached to that selection could be 250,000. It's large numbers that we end up getting to. And the basic idea that we had was that when we had a result come in to say that particular selection had won, then it would be as simple as sending a win message to that process. Or if the price of that selection had changed, it would be as simple as sending a pricing message to that process. And that's essentially the way that we built the first version of the system. Some tuning that we did is we had some horrible results to start off with. Transparent huge pages, they just don't work for the kind of systems that we're building. So one of the first things that we end up checking is, are transparent huge pages enabled? You really want to make sure the square brackets around the never. It's not going to do it. Essentially what you'll see in your system, or what we observed, was that you'll have great transactional attributes of the system, and then something bad will happen and it will effectively stop. It almost looks like Java. Yeah. Another thing that we found really cool about this way of being able to lay out the system, because everything is a mailbox, it's really, really simple to find where the blockages are. So it's basically hunt the queue. And we've got various different utilities within the system that allow us to look and monitor the metrics of the queues within the system. And essentially, a lot of the tuning that we did within the Erlang system was really just finding those bottlenecks. And you find them through a few queues. We got awesome concurrency as well with this model. This was within an hour of having access to this machine. It's a 32 CPU machine, no changes to the real underlying application at all, because we start a very large number of processes. Typical on a Grand National, we might be looking at 6 million processes within the VM. And we just see 32 CPUs just lighting up, and it was free. Well, nearly. Yeah, so there was some stuff that didn't work so well. One of the biggest issues that we had is that in Erlang, message passing is process to process. There's no broadcast. And that doesn't matter when you're sending tens or low tens of thousands of messages, but when we're sending a very large number of messages, so the example of a very heavily backed selection, if you have to send 250,000 messages to another process from that process, you very quickly find that Erlang conspires against you. So it will start deprioritizing that process. There's workarounds that you can do. You can set your priority to be high. You can send the messages and set your priority back to be low. But it feels like we're breaking stuff that we shouldn't be breaking. So that's one of the things that we observed, one of the things that that led us to dislike this implementation, this A version of the implementation. We also found our memory consumption wasn't too bad. Grand National, 6 million bits, about 40 gigs of RAM. Not huge, but it felt wrong. It felt like we were doing the wrong thing because the actual process memory was the main consumer of what was going on. So it was another thing that kind of led us to a different way of thinking about this system. Another issue that we had was that we were spawning lots and lots of children, and we were churning those children. And one thing that we found is that having a supervisor with a very large number of children, 200,000 plus, then when you're churning those children, and it's the combination of those two things, it really doesn't perform. And we were finding lots of issues with the system being slow as a result of that. So we did a bunch of techniques. We've sharded supervisors. We've done all sorts of things. But again, they feel like we're working around really things that are design issues with the way that we've built it. Another issue that we had, and we love gproc. Gproc's great. You can kind of register things, and it doesn't have to be an atom, which is kind of important if you've got 250,000 of them to register. We use gproc a lot. Unfortunately, the underlying implementation of gproc uses ordered set. And the combination of register and unregister in gproc can also cause problems. So there's a really cool paper down at the bottom, more scalable ordered set threats using adaptation, September 2014, I think it was, which basically says, don't use these. And unfortunately, ordered set is the thing that gproc uses, and it very, very quickly stops scaling when you've got situations where you're churning these large number of children. So that was an issue that we fell into quite quickly. We also had another issue where we're reading these streams, and these streams are JSON streams. And one of the things those streams are doing is they're living for a long period of time, because the whole idea of the stream is it's a long-lived connection. And part of the problem is that the little bits of JSON are less than 64 bytes. And if they're less than 64 bytes, then magic seems to occur. And it's not the kind of magic that you like. So we ended up doing things to the garbage collector, which, we're not doing Java, we shouldn't need to do these things. So we ended up doing a full sweep after 5 on the processes that are reading from the stream. So long-running processes that don't do very much apart from cut up binaries and then send the binaries to somewhere else. Not great. So we had a moment of clarity and thought about this a little bit differently. We talked about it for a little while, maybe as much as an hour, and then started a rewrite. And so we started thinking about things, well, maybe if every concurrent activity was a process, maybe that's a better way of modeling this. So we came up with this wonderful thing called BetFlow, which is the current implementation. I'm smiling so much now. And again, very, very high level, very high level. Generally, we have a change that's going through the system. So that's a result change, let's say, and you have a series of steps that we can declare in betflow that allow us, and the circle is representing the process. And the idea is that we end up having a process that handles that change. And it's not a long-running process that's doing it, that actually represents the entity itself. So for a result change, we find the affected bets, and we then resettle them as a process, and then that process dies. For a price change, we do pretty much the same thing: find the affected bets and then reprice them. And it's a process; it lives, and then it's gone. And as I've said, we used sharding for supervisors. One of the things that we've also done is we've used sharding for the ETS tables. So in order to get the level of concurrency that we want, so when we change from a concurrent activity no longer inside the process, what we're now doing is we're persisting our state inside ETS, so keeping it within memory, but instead using ETS to actually persist that data. So the price change comes in, we make the price change, we then persist it into ETS. The issue that we found there is that, again, you have to shard ETS. So the general metric that we've used is for each core we have a shard, and that was very, very scientific. Not at all. It seemed to work. Another thing that we did is, because of the issues that we found with the large number of children that were churning within a supervisor, we switched supervision away from OTP to use Basho side job instead. And that seems to be working pretty well for us. And it's quite a cool library. So this was this Saturday. We have price changes here on the right. You can see that we have 500,000 price changes. Pretty much from about 9 o'clock in the morning, we're pretty seriously getting load, or what we consider to be serious load. And then we have up to 100,000 bets in a 30-minute period. And the cool thing, this version, we're using a huge 1.5 gigabytes of RAM. I mean, that's Hello World in Java, I think, pretty much. And we're using 500 processors. And that's nice and steady. There's lots of very ephemeral processes that are being started and stopped. But it's nice and flat, and we're pretty happy. The thing that's growing, we know that's growing, and that's bad. But the reason why is because at the moment we're not terminating our children, because that's evil. And so instead, at the moment, the ETS tables are growing, so that's the thing that you're seeing that's growing. What we'll do is over a period of time, we'll then start killing those children, which always sounds wrong. Generally, we're pretty happy, but if we're pretty happy, that means we're probably doing something very wrong. So we're talking about how we do it next. So we're talking about a way that we might be able to do this as a hybrid. So there are various different attributes that we've seen of one of the systems that we quite like, and there's other attributes that we like from the other system. So I think we were probably presenting in 6 months' time the third version that we end up with, which is going to be a little bit different. So I wanted to talk a little bit about how we build stuff and how we ship it. This was the quality metric at my previous companies. It compiles, ship it, man, come on. We use Docker. If you don't use Docker, use Docker. It's trivial. I mean, if you've got a relic script, then that's your release. Your release is _rel. You build from an existing container, you expose some ports, and you have an entry point. And if you're using Erlang release process, it's simple. You just build a release. And some of our containers are, maybe a couple of tens of megabytes. They're tiny. It's really cool. Use Docker. Nothing else. Just use Docker. Don't worry about anything else. So what we're looking at is how we can scale this system. And we see Docker as the mechanism of us being able to both horizontally and vertically scale this system, which is all very well and great. Bad things happen. So there was a fire in Gibraltar not so long ago. Ian's flat. Where was your flat, Ian? Was it there? So there was a fire in Gibraltar. It took out I think the one and only power station in Gibraltar, which is reassuring. And most gambling companies were affected by this, which is not good. So obviously we don't want to repeat that. So one of the things that we're looking at is how we can use Kafka to actually do that replication for us. So what we're thinking is data center, data center, data center. And we can then have settlement running in as many locations as we want. The great thing about settlement is anyway, results for races are redeclared. So settlement has to be able to be rerun. So it's something that is very much something where we could actually think about having competing settlement engines. So we might use Kafka to partition the load in different ways and have different ways of doing that. So we're thinking about how we might want a red carpet. Certain customers go to these particular systems, other customers go to different systems. That's certainly something that we could do with this kind of technology, and use Kafka to kind of help us split that load up within the actual data center. Elephant in the room. Nobody talks about this. So I get this asked once or twice a day. Why not Akka on the JVM? So this is a true story, because they're always more fun. And it shows that things go wrong as well as they go right. And I think when things go wrong, it's more interesting than some amazing syntax and stuff like that. So this is our system running normally. We're using, gigabyte of RAM at peak. We're probably trending up from up towards 500 megabytes, let's say. And this is our price changes. And you can see our price changes are pretty much flat. So the load is normal, and everything looks good. We went home. Literally an hour later. This is exactly the same graph, but the problem is that we're now measuring hundreds of gigabytes of RAM. And so the previous beautiful graph that I had there has now completely disappeared because it's no longer on the scale at all. And this was a pretty scary moment because nothing's changed here. You know, the load's the same. These other graphs, they're all the same. Pretty much the input has remained the same. No, 10 minutes. And then we've nothing's really changed. So what's gone on? So there's an awesome book, Erlang and Enger, Stuff Goes Bad. Docker, Erlang and Enger, two things. Read it. It's great. And we use, as part of everything that we build, our stuff, ships of recon, because it makes this stuff simpler. And so the other great thing is that we can SSH into the VM. So we've set up all the VMs that we deploy. One of the things that Docker makes hard is how do you actually connect into the system. So one of the things that we do is we expose an SSH port so we can SSH directly into the VM. So we get a command line straight into the VM, and the first thing that we ran was recon proc count. I'm lying so much when I said the first thing we ran. In retrospect, the thing we should have run first was recon proc count, but we didn't. But anyway, let's pretend we did. And the cool thing about recon proc count, you give it a list, and there's 10 more of these, and it's ugly Erlang syntax, but other than that, it's fine. But the cool thing that you get out of this is you get a PID, so 535102 is important, and this is important. This is 4 and a bit gigs of data in one process. That is not good, and we've got 10, 100 of those going on, and it's the reason why we're using that many gigs of RAM. But the good news is it tells us where are we, backcalc, and it tells us where we started. So things were literally on fire somewhere, I'm sure. And what we did is we ran recon trace calls. We told it to trace backcalc, any function, any arguments, and then here's the important bit, the PID. And this is cool. I'd love to know languages where you can do that in. Because this is a system that is dying, it's about to crash. and we're still able to log into the system. We're able to determine where it's failing. And to me, that's killer. So this is the trace, and there was, megabytes of trace that's flowing past. So this is loaded up into my trusty editor, the one and only true editor. we could see, no. And then you can see the bet ID. And the other interesting thing from this trace is that we can see the index is 26. A lot of the bet calc math is around permutations and combinations of bets, and that's the thing that costs CPU, and that's the thing that costs memory. So we can see the bet ID, we can see the index of the bet, which tells us how big that bet is. And so the next cool thing that we can do is we've got an API within the system. We've got a shell into the system, we're SSH'd into the system, it's on fire, but we can still ask the system what's going on. So we can look up this bet within the system, and we can find that it's actually an accumulated 25, but we had 26 selections coming in, which was important because here's the settlement code. Obviously, I have to kill all of you after showing you this, but anyway. Here's the settlement code, and you can see it's an accumulator, it's of this size. They settle, we have underlining settlement functions for the different bet types. So settle straight line is one of the bet types. And you see here's the settlement for an accumulator, where the size of the accumulator is not the size of, when the size of the number of selections is greater than the actual size of the accumulator, which meant that we were in this function here. And if you know anything about betting, then you know that that number 2 is wrong. And essentially what we were doing was generating combinations from 2 up to 26. So that number should have been n. Now, Recon didn't tell us that, but it was pretty easy for us to get to that point to work out that that was the thing that was wrong. And 20 minutes later, we had a test case, and a day later, we had a fix, and a day later, we had something that was using not how many gigabytes of RAM it was, it's now bytes. So we're a lot happier. So to me, this is one of the killer reasons to that question. It's not about the code. Anybody who's written Erlang code knows that it's not pretty, it's not sweet, it's not as nice as Scala and half a dozen other languages. But to me, it's not about that, because it's all about the operational support. Because if you're a developer, the thing you're worried about is the phone call at 3 o'clock in the morning. And that's, to me, is the killer thing for OTP and Erlang, is that when things are going wrong, there are tools within the system that are there, and they work, and they've been tested. So you get built-in tracing. We've got a utility library that we put in every single, or utility application, we put in every single app that we deploy. And that allows us to SSH directly into the VMs, which if you're on a Docker engine, then it's painful to get in directly. Well, it's more painful than it should be. So it means that we can SSH minus P, and then the port that we want to go to, and we can go straight into the VM. And then the other cool thing is, obviously, with the shared nothing architecture, it means that crashes are really easy to reproduce. So you can basically replay the same state, replay the same message, and you're good. So that's me. Thank you very much for your time. Thank you very much for listening. We're hiring, which is such a surprise, isn't it? If any of this has sounded interesting even, or if you just think we're mad, which would probably be equally interesting for me, then I'd love to talk to you. But if there are any questions, then please feel free. Oh, hello. Greetings indeed. Oh, cool. Thank you very much. Was it good? Awesome. Okay, that's cool. Are you doing similar things, or are you? That's a shame. Any more? Oh, wow.
You mentioned how easy you find real-time diagnosis of systems. I was interested in what you do for testing. Obviously, you showed us one bug you had there, which maybe could have been found at a small scale, but I'm actually more interested in like a full-scale integration testing type thing. Do you do load testing? Do you do other types of integration, full system testing, and stuff like that? Because I'm trying to work out how we're going to do full system testing and load testing.
Do you want to tell us? We're looking at, so the question is, how do we do testing? The bet calculator, it's heavily unit tested. It's hundreds of unit tests. But the problem with that is that there's millions of combinations. So we have looked at, but haven't done anything with yet, proper quick check, and they're the obvious things. So we build the types, and then we build type generators from that, and then we build our test cases. Essentially, the way that we work at the moment is build, unit test, CI. The CI then deploys to, we have 2 identical hardware platforms. We have 2 variants of this system, the 2 that I talked about today, and we essentially run those 2 in parallel, and then we collect data. The graphs that you're seeing were from Elasticsearch. We have another library that we use that basically pokes data into Elasticsearch. So what we do within our systems, we register things that we think are important. So the number of bets, the number of transactions, the number of price changes, and we graph those. So all the things that you saw were graphed through that system, and that's basically sending HTTP requests to Elasticsearch, and that allows us to look back historically and hysterically sometimes at previous data. Good.
Do you have some sort of way of identifying suspicious market behavior, such as huge bets that might influence market or things like that?
So one of the things we're really interested in is identification of strange bets. Yeah. Those streams, they get fed into this system. This system is not a system that we want to be able to do that kind of analytics on. So what we do is we then feed that into Apache Spark, and then we then build systems on top of that then look at suspicious or different behavior. And it's quite interesting to identify some of those behavior. We had a case quite recently where a large number of people were miraculously betting on the correct score for a game in Australia, in the Northern Territories. And yeah, what we're trying to do is identify those cases and identify where that's happening. We're looking at technologies like Spark to be able to do that, not specifically in Erlang.
So is it real time?
Yes, yeah. Any more? Oh, I can't get over there. Last one. Can I? Yeah, thank you.
Now, I don't really know anything about betting at all. But I do know that sometimes it's got something to do with statistics. And people say that Erlang is is slow at numerics. So was that not a barrier?
No, because the maths is quite easy. It's the short answer. So the settlement that we're talking about, it's really a multiplication and an add. And if Erlang can't do that, then it's, well, yeah, it can. That's reassuring, isn't it? So the mathematical modeling that I was talking around our pricing, that's done in Java. So the pricing systems are built in Java. The actual settlement of the bet, building up the combinations is probably the most strenuous bit. And then the actual calculation itself is fairly simple. All good? Thank you very much. Thanks for your time.